As for our next speaker, world's most interesting mathematician, are you there?
Hello, can you hear me?
Oh, yes, I can hear you, the world's most interesting mathematician. There you go. Well, just remember, I want you to remember who's the original one.
I think you said that you said a trio, right? Being the first to be to be named the most interesting mathematician. So I'm just following along those trios.
Yeah, no problem. I mean, I must admit, I did see an article on social media that says it said like this: first African mathematician to be named as world's most interesting mathematician. And I said, what about the African diaspora? Eh?
Yeah, so that would be African of African descent. Yes.
So it's not about the African diaspora, but no problems. Okay, I'm gonna we get to be pulling people in now, so hopefully we can start in about 2-3 minutes time. So we'll be cool, okay?
Okay. I'm not able to share my screen, so if I can be assisted.
Oh yeah, we're gonna make you host, so you can share the screen. We'll get that organized in a moment, yeah?
Okay, I have 2 devices, so
Okay.
which one? The one without audio would be the one I would share my screen on.
Okay, I'll get some. Right, do you want to? Yeah. Are you logged in on 2 devices? Yeah, right, there you go.
But then she brought me back when she applied. Outside of here.
Yeah, we're getting the slide.
All right, I'll see. It was a free year.
Yeah, okay.
Depends on the slides. It's funny, some you said.
Okay, Angela, how you doing?
Just a second, let me try again.
Okay, Mike, this was Angela as well, co-host. There's pictures too. She's got 2 devices. Yeah. Yeah. Right, Angela, we're going to make the other one your other device co-host as well, so you should be able to share that one, yeah?
Oh, okay.
Yes. Cool. Okay. Right. Angela, are you happy?
So one more second. I can see I've made a co-host, so let me try again. Hopefully it works this time.
Okay.
What was I mindful of that? Distribution to get a better understanding. Was spatial stuff, so you got a couple of dimensions.
Right, as Angela's getting ready. Right, we're about to move on to the next session. So what I'm going to do is I'm going to introduce Angela, and then when she's ready, she'll give the thumbs up, and we'll go straight in there. So what I'm going to do is introduce Angela Tabiri. She is the first ever speaker at the first Black Heroes of Mathematics conference. She actually opened it up. Yeah, so she has that proud honour. Here you go. And last year we had a vote amongst our delegates to say which one of our speakers for the last 4 years, would you want to come back and speak in the 5th year? And Angela came out on top. There you go. You don't mention that on social media, but that's the way it goes, yeah? Now, she works as an Ames Google AI postdoctoral fellow at Ames Ghana. And what she has done is that she runs an NGO called FEMAMAS, which is founded to promote African females in mathematics. What they do is that they interview female African mathematicians and share content on social media, such as platforms like Instagram, Facebook, YouTube, Twitter, to inspire young girls that there are diverse career options when you study mathematics. Here we go. Has that bought you enough time? No, okay. And so this is yeah. She
Yes,
did. Okay, she
thanks
did.
so much.
Yeah, do you need me to speak for 5 minutes more and big up for another 5 more minutes? She did a PhD.
Maybe one more minute. I'm still just
Okay.
one more minute. Yes.
One minute. Okay, she did a PhD in Glasgow. There you go. And yeah, and she'll be talking about being the world's most interesting mathematician. There you go. And she's also a representative on the United Nations. Yeah. And one time she even, I think it was yesterday, she was even speaking to the Swiss ambassador in Ghana to show them the value of mathematics. Okay. And one time she was working on she was collaborating with myself and a school in the UK promoting mathematics. Okay. Right, you're making this easy for me. All right, so here we go. Yeah.
Okay, so I think I'll just talk whilst I try to sort this out on my screen. So
okay. And are you ready to go?
I'll start and hopefully I'll be able to.
Okay, because I'm running out of accolades to say. I'm running out of accolades, you know what I mean?
Yes.
I would like to say, and you spell her name Angela, you know. All right, here we go. Angela, the floor is yours.
Okay. Thanks so much, Nira, and thanks so much to the organizers for inviting me again to speak. Like Nira said, 2020, I got my first invitation to speak at the maiden Black Heroes of Mathematics conference, and I spoke about the work I do in telling the stories about female African mathematicians. And today, 4 years later, I'm following the trails of Nira, who was the first person to be named the world's most interesting mathematician, right? So that has also inspired me, as he being a Black hero of mathematics, to go on to win this award this year. So thanks so much, Nira, for blazing this trail, and thanks also for the opportunity to speak. So I had an icebreaker for this. So I guess I'll start off with the icebreaker, and during the icebreaker, I can sort this out. So for the icebreaker, we are going to use Mentimeter. So I'm going to share my other screen. So Mentimeter, we are going to, I would like to hear from my audience where you are from, and a few questions. As a mathematician, usually we come with questions. I was teaching recently at Ames, and usually we like to ask questions during classes. So I'm going to share my screen and put in the code. So we are going to use Mentimeter, where I'm going to share the code so that it can be a bit interactive and I can hear from my audience. Okay, so my screen is shared. Yes, brilliant. So I would like to find out from my audience where you're joining us from. So this an international conference. So if you can go to menti.com and use the code 75686671. I'm also going to put the link in the chat box. So menti.com and use the code 75686671. So for those online, I'll put the link in the chat box. Brilliant, London, right? Yes. So it's great to have the audience from London. Yes. So I think 2 of you are joining from London. It's great to Okay, so Nottingham, okay, so a bit of diversity there. Edinburgh, brilliant. So 3 UK cities. What about the rest of the world? Are we having people joining us from other parts of the world? Ghana, brilliant, right? My home country, yes. Yes, okay. So we have UK, Ghana. Do we have people joining us from other parts of the world? Do you have people joining us from other parts of the world? South Africa, brilliant, right? South Africa. So Ghana, West, South, what are other continents or other cities? Do we have people? I would like to find out which city you are joining us from. Okay, so I guess I'll go ahead since we are behind time. Brina Opavia, okay, so Italy, right? Is great. So Europe, UK, Africa, brilliant. Cheltenham, oh, okay, brilliant, right? So a lot of UK present, but also diverse audience. So let's go to our next question. Yeah, so I'm supposed to be speaking as the world's most interesting mathematician, and as a mathematician, we like definitions, right? So I would like to hear your version of who can call themselves a mathematician. This will require a little short sentence or a paragraph. Who would you define a mathematician to be? Okay, a geeky nerd, okay. Sees a problem and never ever quits, okay. Someone interested in mathematics, okay. A teacher, numbers experts, an inspirator, okay. A person who studies the mathematics behind certain phenomenon, okay. A problem solver, someone who uses or is interested in mathematics, okay. Okay, quite diverse, right? So a person who works with the mathematical sciences. Okay, very broad. A thinker, brilliant. Maybe one more, then we go to our final. A family managing their finances. Okay, wow, yes. Interesting. So thanks everyone for your inputs. And finally, our last question, right? I'd like to find out from you, who would you call your Black hero of mathematics, right? Who would you call your Black hero of mathematics? Who will you call your Black hero? You have Nira there, brilliant one, Nira. Yes, so Nira, here you are, Black hero of math. Oh, okay, my name too. Yes, a Black person, yes. Oh, a Black person. Oh, Fatuma, yeah, I saw Fatuma in the audience. So Fatuma was speaking last year at the Black hero of math. David Blackwell, yes, who our first speaker spoke about, right? So, wow, brilliant. So I'm going to, thanks everyone for your inputs. Hopefully this allows us time to get my other screen sorted. So I'll try again to share my other screen, and hopefully this should work. Okay. So for today's talk, I'm going to talk about our journeys, my journey to becoming the Black hero to becoming the world's most interesting mathematician. So a bit of introduction about me. What do I do? So I am Angela, and I'm a mathematician. My research is in quantum algebra. What is quantum algebra? So quantum algebra is non-commutative algebra, which I will explain in the next few minutes. And I'm also a mentor for girls in STEM. So I work with the African Institute for Mathematical Sciences, AIMS Ghana, where I manage a mentoring program for girls. I've currently directly mentored about 120 girls in the mathematical sciences who have gone on to pursue STEM at the university. So our graduates, they come in at the high school level just a year before they go into the university. And so far we have about 120 girls. Some of them have moved on to the UK to study mathematics and other parts of the world. And our goal is that over the next 10 years, we want these girls to be the ones who will be leading in research and in innovation in the mathematical sciences. And yeah, so I work with AIMS. So AIMS is the African Institute for Mathematical Sciences. We have Pan-African Centers of Excellence across Africa, in South Africa, in Senegal, in Cameroon, in Ghana, and in Rwanda. And at AIMS, so I'm a Ghanaian. I did my master's at AIMS about 10 years ago. And afterwards, I was looking for opportunities to do a bit more maths. And one of my mentors, Uli, so he was teaching at Ames and he told me about ICTP. So ICTP is the International Center for Theoretical Physics. It's in Trieste, Italy. And I went to ICTP for a year to do their postgraduate diploma in mathematics. And it was at ICTP that I realized, okay, if I wanted to study maths, I really needed to learn a lot, right? Coming from Africa, moving into another educational system was quite a tough environment, but there I learned a lot and I applied for my PhD funding. So I applied for the Schlumberger Foundation Faculty for the Future Fellowship, which is now open. So I say this because it supports women in STEM from developing countries to study at top universities abroad with a goal that we return to our home countries to promote the teaching and research in the STEM courses. It's currently open till November. So if you're interested, it supports PhDs and postdocs for women in STEM. So I went to Glasgow for 4 years. Kenny, my supervisor, maybe he's online, and Uli. So I did a PhD in math, graduating in 2019. So after graduating, I love Ghana, so I returned back to Ghana and I got my first position as a postdoctoral fellow. So as an Ames Google AI postdoctoral fellow at Ames Ghana. So as a postdoc, I was teaching at Ames. So at Ames, we have regular master's programs and I started teaching a course in linear algebra, but we also have a course in AI, a master's in AI, the first in Africa. So it's the African Masters in Machine Intelligence programs. And I was teaching a course in mathematics for machine learning, which was very eye-opening in the sense that my research is very abstract. I do algebra, quite abstract, but I was faced with the challenge of teaching a diverse group of graduates, linear algebra, calculus, these skills that intuitively they will need to become machine learning experts. And it gave me a very new tool of teaching in the sense that if you are teaching an abstract course, it's important to do the rigorous definitions, but it's also important to teach in a way that students will have intuition. When they see something, they should know what it could be, whether is this true or not, then they go on to prove it in terms of pictures and also formal ways of doing things. So I started as a postdoc, but during my postdoc, we started this new program, which I was mentioning, the Girls in Mathematical Sciences program. So after my 2-year postdoc, I transitioned into an academic manager where I manage our Girls in Mathematical Sciences program. So this is a 9-month mentoring program for high school girls in Ghana. And the goal is that we want our girls to see a lot of modern problems in mathematics with the goal that they go on to study maths at a university and go on to do research in maths, but also work in industry. So we started this in November 2020 with 35 girls from 11 regions of Ghana. So in Ghana, we have 16 regions. So in our first call, we did quite well, covering more than half of the country. The girls came into the program. First, we gave them a laptop, which they could join online sessions with. We gave each of the girls a mentor. So a mentor was an outstanding woman in STEM from across the world, not just in Ghana, but also we met them online for online master classes. So Nira, you do your talks where you go to schools, right, to talk about maths, and we invite online speakers to speak. So for instance, Yolanda, who was one of the speakers at the Black Heroes of Maths conference, she spoke to our girls. And the goal is that we want them to see that maths goes beyond what they see in their classroom and their modern topics that they can do in maths. We do this usually on a weekend, so once every month on a Saturday, because they're in boarding school, we don't want to disrupt their academic processes. So we do it on the weekends, and online speakers speak. So if you're in the audience and you'd like to speak at our online master classes, I'm happy to speak with you. But also when they're on vacation, they come to our campus. So At AIMS, we are Center of Excellence with 24-hour learning environment. So we let our girls who are in high school, they come into our campus, and we teach them advanced mathematics. So there was a year that we were teaching our master's students vectors, linear algebra, on one section of the classroom, and on another section, we had these high school girls learning about vectors. It was quite interesting seeing that they were passionate about math, they had the competencies, and we just had to expose them to a bit more math. So I transitioned into managing that, but we also have a master's program for teachers. Why? Because in Ghana, when you finish your senior high school, you write a national exams. It's not just in Ghana, it's across West Africa. We call it the West African Senior Secondary School Examination. And every year, when the results are released, mathematics is one of the subjects that a lot of students fail. And as an institution of maths, we wanted to change this narrative, which led us to start the Masters in Mathematical Sciences for Teachers. So this is for high school teachers in Ghana. It's mainly online. So because they teach full-time, we meet them after lessons. So in Ghana, lessons usually end at 2 p.m. So our lectures are from 4 to 6 p.m. our time, and they gain the same skills that our regular master students gain. We first start with skills. They learn how to code, Python programming, mathematical problem solving, physical problem solving. Then they go on into specialized courses. For instance, in the review phase, they do courses in data science. They do courses in financial mathematics. We want them to understand the foundations of math so that they will improve the teaching and learning of mathematics in high school. So I've transitioned into managing this program here at AIMS. So if you're interested in teaching in any of the courses, we are happy to speak with you. But also, if you are interested in supervising essays, we are happy to speak with you. So then now back into why I was invited here. So the big internet math-off, right? So in May this year, I received an email from Christian, Law Perfect. So Christian organizes the big internet math-off. So it's a competition, online competition for mathematicians across the world. I'm 16, and at each round, you are supposed to pitch an interesting math idea, and the audience is expected to vote for you. And when I received the email, I was a bit skeptical that, okay, will I be able to win this, or will I be able to pitch interesting ideas that will get me to the round? But one thing that encouraged me was that someone had nominated me. So someone in the room, Nira, had nominated me to compete here. And for me, that nomination, when someone nominates you, it means that you have what it takes to win. All you need to do is to put in your best. So I said, okay, I'll take up this challenge and follow on the footsteps of Nira. So in the competition, we have 16 mathematicians from across the world. I was the only one from Africa, and for me, I was like, okay, let me see how I can pull this off. So it started with pitching ideas at each stage. So for my first pitch, my goal initially, so I consider myself as a science communicator, and as a science communicator, I try to demystify the mathematics that we do. So in terms of my experience, I mentioned I taught a course in mathematics for machine learning. So very often when I'm teaching a course in linear algebra, I use very practical things. So if I'm teaching, for instance, something on vectors, right? We start with thinking of vectors as containers that we store information in. Now, if you the attributes will be in terms of what rows or drawers that you store them in. So if you have a drawer, a cabinet with 3 drawers and another one with 4 drawers, can you add them? No. So which gives them some intuition about if you have a vector with 3 attributes and another with 4, you cannot add them. So I did this first pitch on mathematics for machine learning. also relating it with ChatGPT, right? So we all use ChatGPT and how it's also built heavily on mathematics. People found it interesting and they voted for me. I guess that was the highest vote I got for the competition. So they voted for me massively and I made it to the next round. And in the next round, I was pitched against Howie. So Howie was he does a lot of high school math tricks with lots of following on social media. And for me, that stage was quite challenging because you are pitched against someone who has a lot of following with interesting facts, but I had to pull off some interesting bits from my bag, right? So at this stage, I talked about my research in quantum algebra. So the UN has declared the year 2025 as the International Year for Quantum Science and Technology. And I wanted people to understand when we say quantum, it sounds like a very big word, right? But it's something that we all see around us. So let me try to convince you of that. So I started by first appearing with wearing a shoe first before a socks and a socks before a shoe. Now, if you look at these two pictures of a shoe before a sock and a socks before a shoe, you realize that they are different, right? Which meant that the order in which you wore these two objects mattered. But when you think of addition, 2 plus 3 is not the same as 3 plus 2. Sorry, it's the same as 3 plus 2, right? So the order in which we add doesn't matter. So in maths, we call things where the order doesn't matter commutative. But things that the order matters is non-commutative. So the shoe and socks example is a non-commutative example. You can think of subtraction and division. These are all non-commutative. So my research involves curves. I'm still trying to share my screen. In case I'm able to, I'll draw. I'll write. But so in my research, we look at plane curves. Now, if you consider a ball, a football, every point on a football looks the same because it's curved the same. So in mathematics, we say it is homogeneous. But now if you consider the alpha symbol, right? If an ant is walking on the alpha symbol, it will be walking on a straight line until it gets to the point where the two lines meet, then it will have 4 options to go to. So that point in the alpha symbol where the lines meet is special, so it cannot be homogeneous. So we have to make it somehow homogeneous. How do we do so? We do so by looking at a certain structure which we call a Hopf algebra. What is a Hopf algebra? So think of, I would think more of dictionary. So let's think of, we are trying to build a dictionary where the dictionary involves words in certain alphabets. So for instance, I can build a dictionary with words in alphabets X and Y, A and B. Now, this dictionary is also highly non-commutative. Or you can think even more broadly if you look at dictionary of all possible words in all alphabets. So in the English language, for instance, if we look at the word face, F-A-C-E, like my face, right? The alphabets are F-A-C-E. But if I rearrange the alphabets in face, I get cafe. So the order in which we arrange alphabets in the dictionary would usually change the meaning of it. So even the dictionaries that we use is highly non-commutative. So my research looks at plane curves, and our goal is that because there are certain curves which have special points, they cannot be homogeneous, but can we make it somehow homogeneous? And if you are able to do so, we call that a quantum homogeneous space. So that's what my research is. And what things do we need? What ingredients do we need to do this? So we all know, have heard of prime numbers, right? Prime numbers are usually thought of as the building blocks of the number system. So we have the fundamental theorem of arithmetic that if you are given any positive integer greater than 1, you can either tell whether it's a prime number or you can write it uniquely as a product of prime numbers. So prime numbers are the building blocks of the prime number of the number system. But if we look at another version of another structure, so for instance, in our dictionary, we are looking for special words that every word in that dictionary can be written as some combination of it. So you can think in terms of a vector space. So a vector space, and if you all vector spaces have a basis, right? So a basis is more of the building blocks that every vector in that vector space can be written as a linear combination of it. So as a similar one, we have that. And if those properties are satisfied, then we say we have a quantum homogeneous space. So my pitch for the second one, I talked about a quantum world, just to highlight that most of the things around us are non-commutative, just like the English dictionary. That's also went quite well. Howie was winning at some point, but at another point, I overtook and I won that round. And for me, that was quite a turning point, right? Once Howie, I won that round, I knew, okay, I was just 2 steps away from winning. So I needed to put in a bit more. Then for the semi-finals, I was pitched against Aileen, and Aileen has a lot of following also on YouTube and on social media. And for me, for that pitch, because I had talked about quantum quite abstract in the previous pitch, I wanted to do a bit something more everyday examples. So I gave 6 everyday examples of maths. Starting from, so I live in Ghana, and I like to use my environment as examples of motivation. So in Ghana, in the mornings, usually people buy street food for breakfast. There's this porridge that is served on the streets, and it's usually sold in a cylindrical container, so something cylindrical. And if this seller, who is in the informal sector, would like to find out the volume of porridge in that cylindrical container, the person can think of it as, okay, if I look on top of my porridge cylindrical container, it looks like a circle, right? And if I want to find the volume in this cylinder, I can think of adding the circle, the number of times of the height, right? And that is how we calculate the volume of your cylinder, right? So I gave that example, but another example of we learn about modular arithmetic in school, and it looks very abstract, right? But we can think of the clock. We live in a 24-hour Earth, but our clock has 12 hands. So currently it's 14:31 here in Accra, Ghana, but we usually write 2 p.m. How do we arrive at this, right? We divide 24 by 14, and the remainder is 2, which we say that is what, 2:31 p.m. So I gave some of these examples, and I made it to the finals. And for me, making it to the finals was okay. I needed to up my game, because all this while I'd been talking about more general ideas. I needed to bring out some interesting maths facts in a very specialized way. So in that final pitch, I spoke about pi, but also bringing together what other contestants had talked about. So the number pi has, if we write down the digits of pi and look at the prime chunks of these digits, right? I wanted to highlight this interesting fact about prime numbers, that if you have any prime number greater than or equal to 5, if you square that prime number, the result is divisible by 24 with a remainder of 1. So we think of prime numbers as being random, right? As yes, being random, but it turns out that all prime numbers greater than 5 have this interesting property. So I highlighted that, and my fellow contender, Matt, had spoken about golden triangles. So I tried to bring in the golden ratio, and yeah, that was quite challenging, right? But people found both pitches interesting. I've read some comments online that even people who voted for the other contender found the other one interesting. And in the end, it's a worldwide competition, right? It wasn't just people from your circles or your country voting, but it was a general worldwide audience, and I believe most of them found mine to be very interesting and devoted for me to become the world's most interesting mathematician. So that was a bit about the journey to becoming the world's most interesting mathematician. But I'll still try to. So I think the challenge is because the meeting is being recorded, I'm having challenges with the screen settings on my device. So I don't know if someone could assist me on this so that my last few minutes I could show my slides. So it's yeah.
We've made Angela co-host, so she should be able to share. It's not a problem this end.
Yeah, we've made you co-host on both your devices, so you should be able to share.
Okay.
Yeah. If not, Angela, your presentation style has been very good. You know, no PowerPoint, no cue, just talk straight down the camera. It's very effective, and you like it. So maybe continue like that.
Yeah, but I would also try to use the whiteboard. Maybe that will work.
There we go.
Okay.
Here we go.
Okay. Yes, brilliant. So that works. So I'll just go to what I had prepared to speak on. So I wanted to highlight a bit about my research. So I talked about my journey, but also I want to talk a bit about the research I do. So I'll start from numbers. Okay, so let me change the color. I see green here, so I think I'll just use black here. Okay, brilliant. Okay, so in my research, okay, so I'll talk from numbers to alphabets, okay. So when we are growing up, we learn basic things, starting from what counting, then we move on to abstract things, right? And I think of the research I do in terms of the abstraction of the things that we do. Okay, so when we learn about numbers, you can think of a lot of number systems, right? So you can think of integers, right? So by integers here, we mean what? Positive and negative whole numbers, right? You can think of natural numbers, right? So starting from what? 1, 2, and the rest, right? But after building these number systems, we try to put structures on it, right? So we try to put what? Abstract structures on these. How? Now, when we learn about numbers, right? After learning about numbers, we learn about what? Addition, right? So what do we put two numbers together to get what? Another number, right? So after learning about addition, we usually will learn the reverse of addition. So addition and the reverse of addition. So by the reverse, so I'm using these words carefully in order to get the structure I'm looking for. So if we think of let's say if we think of 2 plus 2, then the reverse usually will be what do you do to get it to 0, right? So let's say 2 minus 2. So it's the reverse is subtraction that I mean, but I'm putting this quite carefully so that I can get the structure I'm looking out for, right? But there's also this other structure of what? Identity, right? So in our number system, if you think of the natural numbers, there's no number that if you add to a number, it remains the same. But if you think of the integers, then there's always the 0, right? That if you add 2 to 0, it still gives you 2. And finally, we can think of something which we call what? The inverse, right? The inverse of the number, in the sense that what number do we add to another number to give us the identity of 0? So if you think of 2, if you add minus 2 to it, you get 0. So we build a structure which we call, so if you have a set which satisfies all these structures, then we call it a group, right? But we go further, after we have a group, we go further to build other structures on these groups. So for instance, if you have a group and addition, right, we can go further to see if we multiply these numbers in the number system, do we still have all these properties satisfied? So in that sense, the reverse of, when you come to multiplication, the reverse of multiplication now becomes what? Division, right? It now becomes division. So you can check all these other structures, and when all these other structures are satisfied, then we call it also a group under multiplication. So we first build our abstract structure of a group. You can think of the integers, but we could also go further to look under multiplication. Can we still multiply and divide these numbers? If you're able to do so, then of course, except the zero, right? Because we can't find the inverse of zero, then we will have another abstract structure which we call field, right? So fields, you can add, divide, and do everything. Now, if you think of the integers, right? There's no other integer that you multiply by 2 to get 1. So it wouldn't be a field. But if you think of the rational numbers, then that will also be 1, right? So we built all these abstract structures. From the field, we can build another structure which we call a vector space. So a vector space, so think of vectors as objects that we can add or scale, right? So, or think of vectors as what? Arrows in space that we can add or scale. So after building these structures, right? Why do we care about these structures? We care about them in the sense that, as I was mentioning, vector space have a very nice structure in the sense that any vector in this vector space can be written in terms of what? A linear combination of a basis. So the basis is just what? The building block of that vector space structure. Brilliant. Now, what about why should we care about this? So in my research, I looked at relationships between algebra and geometry. So in the sense that, okay, so we look at relationships between algebra and geometry. Okay. So my research, so I'll finish very shortly. I just wanted to do a nice picture of my research. Yeah, so I'm an interested mathematician, right? So I just want to highlight what my research is about. Okay, so as I was mentioning, we have this. So as mathematicians, we work in different fields, right? Some work in geometry, and others work in algebra, right? But usually things from one can be translated into the other. That gives you very nice theories so that you can think in terms of one. So I was giving that analogy of a ball, right? So if you think of a football, so think of a sphere, and if there's an ant walking on this, it wouldn't notice any special point on it, right? Because every point on the football looks the same, right? But if you consider, so in maths, we call this homogeneous. Okay. So as I was mentioning, with my hands waving, if we consider the alpha symbol here, right? Now, every point on the alpha symbol looks the same. So if an ant is walking, it wouldn't notice anything until it gets here to this set here, and it will realize that there are different places it can. So it cannot be homogeneous, right? But we can think of making it homogeneous, right? So we can think of making it homogeneous by putting some non-commutative structures. Okay, so here we put something non-commutative on it, right? And it becomes homogeneous. Okay, so this is me talking loosely, right? So my research looks at curves like these. Now, I've written this as a picture, right? But these curves are given by equations, right? So equations in the sense that this curve here can be written as the equation y squared equal to x squared plus x cubed. So your y-axis and your x-axis, right? So in our research, we were looking at curves like this. So another example would be, for instance, a curve similar to this, right? Which is the cusp. So y squared equal to x cubed. Another one would be this other curve, the lemniscate, which is given by y squared equal to x squared minus x to the power 4. We call this the lemniscate, right? Or the figure 8, right? So my research looks at curves like this. Now, if you look very closely at these curves, there seems to be a pattern, right? Now, if you look here, so let me see if I can get a new color. Now, if you look here, you realize that all your functions on your left are functions of just what? Y. So you have, okay, green is not too great, so let me use this. So you have a function of y being equal to, and all the functions on your right are just functions of x. So you don't have any mixed term in there. And we got a very nice theory. So these curves, they turn out to have a name. They are called decomposable. Decomposable in the sense that you can write one as a function of y equal to a function of x. And in my research, we are working towards showing that all plane curves, so by plane curves, we mean curves with equations in x and y, are quantum homogeneous spaces. We've made some progress, right? By showing that curves to degree 4 or 5 will satisfy this property, but we are looking more general to prove these. Why should we care about these, right? I think that will be one of the final things I would say before I end. So why should we care about this? We should care about this in the sense that, I mentioned that these are quantum homogeneous spaces, which have actually, in more rigorous terms, they are Hopf algebras. Okay, so these are Hopf algebras. Okay, so Hopf algebras, just think of some non-commutative. So think of the words we talked about, right, which were non-commutative, right? And they have found interesting relationships and applications and even in real life. So one of the recent publications we saw was in linguistics, right? Where these abstract Hopf algebra structures are appearing there. In the sense that these Hopf algebras, you think of words, right? Multiplying words to form words, but also there's this other structure we talked about, splitting words. So here, multiplying, and also splitting. So splitting in the sense that if you splitting words, you are trying to find words which combine to have given you a previous word. And there are articles online. I'll try to see if I can share the links online, which have found relationships between these abstract Hopf algebra structures and linguistics. So my research is quite abstract for now, right? But my goal is that we are building all these theories, right? And with time, they'll find real life applications. And before I end, I need to say this. On my slides, I had this African, since we are celebrating Black History Month. I had this African proverb which says it takes a village to raise a child. In the sense that I'm saying this to highlight that I talked about my marriage journey, right? Talking about the places I've studied at, or the opportunities I've, and even this whole world's most interesting mathematician is taking a very big community to win it, right? In terms of even getting nominated. Thanks, Nira, for the nomination, but also the support in terms of the voting, in terms of, in terms of everything. So I would like to say thank you to everyone. Many people I haven't met in person, but they've really been supporting. So thanks everyone for really supporting me along my pure maths journey, but also along my science communication and more general journey. So thank you very much. I tried to manage despite the technical challenges, but I hope this was okay. I'll just pause here and maybe allow for some questions if there's time. So thank you.
All right. Angela, I have to say, that was very good, but I'll tell you, one of the most amusing things I had was when I typed to you, you got 5 minutes to go, and you replied openly and says, I'm the world's most interesting mathematician, I'm going to talk about mathematics. I felt that really was funny. Right, so very, 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 very good. And as I said before, it is very the reason you got voted as world's most interesting mathematician because you actually, with that, just stood directly into the camera and just talked mathematics with it's like it was almost like unplugged mathematics with hardly any PowerPoint presentations, any gimmicks, just talked about mathematics. And a lot of people just wanted to hear and heard your passion about mathematics. But what I'm going to say is congratulations for becoming the world's most interesting mathematician. Thank you very much indeed.